All right, let's see where we are and where we might have gotten stuck at. First part was straight up copying from yesterday. We had our observed values, our expected values, and we had calculated our test statistic as 10.745. Everybody good on that piece? Cool. Checking our conditions. Did we meet the random condition? Yeah. I bought that one bag of M&Ms. We consider that to be a random sample of all M&Ms because they just mix them all together and fill those bags randomly. Do you think we met our 10% condition? Yes. 634 is less than or equal to 1/10 of all the M&Ms. And then we get to large counts. So large counts, if all of our expected counts are greater than 5, then we meet our large counts condition. When we do t-testing, we need to look at central limit theorem, 30 or greater. For chi-squared testing, we want all of our expected counts to be 5 or greater. So as long as your lowest one is greater than 5, you've met that condition. So you would write down, here's my lowest expected count, it's greater than 5, all my expected counts are greater than 5. That is something that's different than when we do z-testing or t-testing, so for proportions or means. This large counts condition, for everything that we've done so far, it's so that the population, or so that we can assume that our sampling distribution is approximately normal. We're not looking for approximate normality here. This is so the sampling distribution is approximately chi-square. And I'm going to hop over real quick to look at that reference page that you guys have. So the formulas and tables and the reference page all the way on the back was where we had looked at that chi-square table. And notice that one looks markedly different than our normal distribution. Just real quick before we go on, why do you guys think it has this shape to it? What are we doing to the data that would give it this kind of a shape? What did you say? We're putting the data together. We do our observed minus expected, right? And then what do we do to the observed minus expected? We square it so that we're never getting what kind of data? Negative. We're never having negative values. So the chi-square table starts at 0. And we only have a tail off to the right because we don't have any negatives from doing that squaring. That's why all of our data is right here, and then we've got that tail out. Or the bulk of our data, sorry, is right here. And then we have that tail out that way. Does that make a little bit more sense there? Okay. Let me pull this back up. All right, so large counts for a chi-square test, so the sampling distribution is approximately chi-square, not approximately normal. We talked about this part yesterday too. The degrees of freedom is our number of categories, not our sample size. Our number of categories minus 1. So we had a degrees of freedom of 5. We already wrote down our test statistic. And we talked yesterday about how to find the p-value. We didn't use table C, we used our calculators. So far, so good on all of that? Cool. Did we reach a conclusion yesterday? We didn't write it down, but did we reach one? Yeah. What did we conclude? We failed to reject. Assuming the null is true, the claimed distribution is correct, there was a 0.057 probability of getting chi-squared of 10.754 or greater purely by chance. So this is, when you're talking about interpreting your p-value, it's a chi-square score. And it's always going to be or greater because we only have that tail out to the right. Because 0.057 is greater than 0.05, we fail to reject the null, and we do not have convincing evidence that the claimed distribution of M&M color is not true. Question 5 on the front side, which color M&M had an observed value farthest from the expected? That was our green, right? There were 25.56 more than expected. All I did was subtract what we observed, what we expected. What was that difference? Green M&Ms were the ones that contributed the most to our chi-square score here. Because we had this difference, we divided by our expected, and then, we squared it and then divided by our expected. And I'm trying to remember exactly what it was. Does anybody have that, like when we added up the column? 25.56, and then we squared and divided. What was it after we squared and divided? 6.44. So 6.44 out of this 10 came just from our green M&Ms. Most of that chi-square score came from just the green M&Ms. This is called a follow-up analysis. It's really important to include this follow-up analysis sentence if you have decided to reject the null. If you've decided to reject the null, we want to talk about where did most of this come from? So you're always going to have the one with the largest difference. Which one is contributing the most to that chi-square score? Page 6 was a lot of the same information, but this is walking through that 4-step process that you guys would be expected to do for a chi-square test. What were our hypotheses? Yep. Null was the claimed distribution of M&M color is true. The alternative was? It's not true. It's not true. What significance level were we using? 0.05. The name for this test is the chi-square test for goodness of fit. So again, the backside, I know it's a lot of repeated information, but the backside is the formal 4-step process that you guys would need to go through. Checking our conditions, we did that on the front side. We have our random condition, random sample of M&Ms. Why do we care about randomness? Generalized to the population. What was our population here? All M&Ms. We met our 10% condition. There's at least 6,340 M&Ms. Why do we care about that 10% condition again? Yes, sampling without replacement so that we have some independence. Third condition is a little bit different here. A lot of time we've called it large counts normal. We're not looking for normal. We are looking for large counts here. All of our expected counts were greater than 5. It's a good idea to name what your lowest one is and show that that one's greater than 5. And then you've got that all of them are greater than 5 without having to list out every single one here. I had this down on the other page. Why do we care about large counts for chi-square? Yes, sir. Yes. So that our sampling distribution is approximately chi-square, yes. This is the only one that we're not looking for normalcy on. Before I show you my picture for this, when we've drawn pictures in the past, they've always been approximately what? Approximately normal. So we drew something that looked kind of like this. We're not approximately normal anymore. Now we're approximately chi-square. So I'm going to draw something that looks more like this. So there's my picture. Always starts at 0. Because again, if we're squaring our observed minus expected, we're never going to get negative. So it starts at 0. You do need to label that. Big bump of data at the front and a tail off to the right. It's not always easy to tell exactly where you should put that test statistic, where you should put your chi-square score. It just needs to be to the right. It's not normal, so we don't put n. It's not a t distribution, so we don't put t. This is a chi-square distribution, so we put chi-square. So the fancy looking x with a squared. Degrees of freedom, just like we did with our t. If you add that, will it be bigger than that? Pretend that was a 6. If you add 6 to this, will it be bigger than 6? Okay, then it doesn't get that. You would need to show your work. This is how you calculate your test statistic. Specific formula here. Show what you're substituting into. And then we calculated our p-value. This is the same calculations that we did yesterday. It's just written out this way instead of written in columns. It's exactly the same thing that we did. And then your conclusion on the back side should be pretty much the exact same conclusion that you wrote on the front side. So I just copied exactly what I had on the front side for my conclusion. What parts of the 4-step process did we have missing here? Parameter was definitely one of them. We always define our parameter, but on chi-square we don't. Jenna, did you have an idea? Same one. Yes, sir. General formula. We only have a specific for this one. There was one other thing that I noticed that was missing that we have had for every other significance test that we've done. A statistic. When we do a chi-square test, we only have a specific formula. This is the only one where we do not have to define our parameter of interest, and we don't have a statistic. So big ideas for today. Kind of sums up yesterday and today in one. Chi-square goodness of fit significance test. We have to state our hypothesis and our alpha level. Our plan, the name of our test is chi-square goodness of fit. You can abbreviate that. Same 3 conditions as always, but large counts. We're not looking for normal. We're not looking for more than 30. We need all of our expected counts to be more than 5. Sorry, that actually has an or equal to underneath it. My apologies. I forgot the or equal to there. Greater than or equal to 5. In our do step, I forgot my summation here too. Good grief. Let me write this down again. Chi-squared equals the summation of observed minus expected squared divided by expected. For all of the significance tests, you do need to include a picture when you are calculating your test statistic and your p-value. Just because the directions don't say to draw a picture, if they say calculate the test statistic and the p-value, it is understood that a picture is part of that. In your conclusion, you're going to interpret your p-value. You're going to reach a decision and a conclusion on the alternative hypothesis. In your conclusion, you always have to say we do or do not have convincing evidence for our alternative hypothesis. Follow-up analysis is important if your results are statistically significant. So if you decided to reject the null, then you need to find the largest component of chi-squared. Which one was the farthest from expected? Which one is contributing the most to that chi-square score? And explain. Once you get this copied down into your notes, I want you to try the check your understanding 4-step for that situation. While you guys are working on that, I'm going to pass back your tests from Friday so that you can see how you did, see any comments that I made. I do need to recollect these from you. After you've had a chance to see your test, we'll go over the check your understanding. And then I'll recollect your test from you. All right. What would our hypotheses be in this situation? Yes. No would be the light is functioning according to the claim distribution, or the light is red 80% of the time, yellow 5%, green 15%. If you just wrote that it is functioning according to the claim distribution, that would be fine. And the alternative would be it is not. The light is not red 80% of the time, yellow 5% of the time, and green 15% of the time. Or the light is not functioning according to the claimed distribution. That would also be fine. Significance level. 0.05, that's usually our default. Name of our procedure. Yes, chi-squared GOF, or chi-squared goodness of fit. Do we meet our random condition?
Yes.
Yes. Give me evidence.
200 randomly selected times.
200 randomly selected times. Why do we do that? Why do we care about our randomness? So we can generalize. What would we be generalizing to? What is our population here? We had 200 randomly selected times. So our population is all times. Do we meet our 10% condition? Would there be at least 2,000 possible times to snap a picture? Yes. So we meet our 10% condition. Why do we care about that? Yes. We care about this for our independence condition. This is so we can sample without replacement. Do we meet the large counts condition? Yes. I calculated the expected counts, 80% times 200. We would expect 160 red. We would expect at least 10 yellow. We would expect 30 green. So all my expected counts were greater than 5. I went ahead and wrote them all out. You could just say smallest is yellow, 10, greater than 5. All of my counts are greater than 5. And why do we care about that one again? Yes, approximately chi-square. If you want to, snap a quick picture of this. And then we will look at the work and the conclusion down here. What is the specific formula that we're going to use? Yes. Chi-square equals the sum of observed minus expected squared over expected. So I calculated that out. Thankfully, we only had 3 categories, so I only had to sum 3 different things. And I ended up with a test statistic, a chi-square of 10.489. I've got a box around this 8.533. Why do you think I drew my attention to that? That's the one that is contributing the most to that score. At this point, I don't know whether I'm rejecting or failing to reject, but I'm going to go ahead and identify which one is the farthest from expected, which one is contributing the most to my chi-square score. So again, test statistic, 10.489. What's our degrees of freedom this time? 2. We had 3 categories, so we have 2 degrees of freedom. So my picture looks like this. Starts at 0. This is the only one that starts at 0. Chi-square, 2 degrees of freedom, 10.489 is my test statistic. My p-value was 0.0053. What does that p-value mean? We're going to reject the null, but interpreting the p-value, what would a p-value of 0.053 tell me? Yes.
Assuming the null is true, there's a 0.0053 probability of getting a chi-square of 10.489 or greater pretty much.
Yes. Assuming the null is true, that the claimed distribution is correct, there is a 0.0053 probability of getting the chi-square score that we saw, of having this observed value, or greater purely by chance. So I heard reject null. What does that mean about our alternative? We do or do not have convincing evidence? We do. Because 0.0053 is less than 0.05, we reject the null and we find convincing evidence that the claimed distribution of light color is incorrect. Because we rejected the null, we need to do a follow-up. which piece of this was contributing the most? I know it's this 8.533, but what does that mean? Where did it come from? Was that red, yellow, or green? That was my green. The largest component of chi-square is 8.53 because the actual number of green is far less than expected. Please make sure that I get your tests back from you guys before you leave the room. Make sure you hand them directly to me because I've got other stuff in the baskets up here.